So let's evaluate the integral from 1 to 3 and from 1 over y to y of root y over x e to the root xy dx dy. So here I've graphed that function, and the blue region below is just these bounds that we're integrating it over. So let's make a substitution. So we'll make the substitution, looks like u equals root y over x, v equals root xy. That would be a good substitution. So then to solve these for x and y, we can see that well, u times v would give us, so the x's would cancel out, and then the y's would get squared. So y is equal to uv, and then for x, we do a similar thing. If we divide v by u, then the y's will go away, and we'll get square root of x squared. So now we have x and y in terms of u and v. So then we need to calculate the Jacobian. So j of uv, we have our determinant of, so let's see, so del x by del u will be negative v over u squared. Del y by del u will be v. Del x by del v will be 1 over u, and del y by del v will be u. So this will give negative v over u, and then minus another v over u, so minus 2v over u. And since we need to take the absolute value of this in the substitution formula, well, since v over u is equal to x, and x is always positive, the absolute value of the Jacobian will be 2 v over u. So this negative sign will go away when we take the absolute value. Okay, so then we need to also find the new bounds, so the u and v bounds. And I think this is the part that people struggle the most with. So let's switch over to the 2D view. So here I've drawn our original region R in blue. So blue will be xy coordinates, and green will be uv coordinates. So if x is equal to v over u, and y is equal to u v, then these inequalities we can just substitute in to get, okay, 1 has to be less than equal to u, v has to be less than equal to 3, and then here 1 over uv has to be less than equal to v over u has to be less than equal to uv. But now we need to work a little bit more with these. So the second set of inequalities, let's handle these separately. So this one will get rid of this. So we've got a 1 over u on both sides. So 1 over uv less than equal v over u. Well, we can just multiply both sides by u, so we get v greater than or equal to 1 over v. So 1 is less than equal to v squared, and then since v is greater than equal to 0, we get 1 is greater than or equal to v. we can do a similar thing with this one. So this will give us 1 over u less than equal to u. And then again, we'll conclude that 1 has to be less than equal to u squared, and therefore 1 has to be less than equal to u. So now we know that v and u both have to be greater than or equal to 1, which will... So let's pick one of them to be sort of the outside variable. So if u has to be at least 1, then v will have to be between 1 and 3. From this equation, v can't be... If u is at least 1, then v cannot be any more than 3. And then we have this bound, 1 less than equal v less than equal 3. So then if we fix v, the first inequality we can then rewrite as 1 less than equal u less than or equal to 3 over v. So summarize our bounds for uv, and so we sort of work everything out, are 1 less than equal to v less than equal to 3, and then 1 less than equal to u less than equal to 3 over v. So here's that region in UV coordinates, or what we called in the lecture, we called these like R and G. And you can try moving the point UV around, and the output XY will lie in the blue region exactly when the point UV is lying inside the green region. And then also in red and purple are sort of the kind of like coordinate lines, or sort of like the axis lines for this coordinate system. Okay, but now that we've got figured out the bounds, we can go back to our problem and evaluate the integral. Okay, so our integral is going to become this will be integral from 1 to 3, integral from 1 to 3 over v, u e to the v, then the Jacobian term, or the absolute value of the Jacobian, is 2v over u, and then that du dv. And then this function in the UV plane is also graphed now. So this just becomes integral. So inside we get these guys cancel out, so we're just integrating 2v e to the v. Okay, so this is integral from 1 to 3, integral 1, 3 over v, v e to the v, du dv. Then that doesn't involve u at all. So that'll be 2 times integral 1 to 3 of 3 e to the v minus v e to the v dv. And we can do integration by parts. So integral of v e to the v dv is v e to the v minus integral of e to the v, which is e to the v. Okay, so our integral is now 2 times, let's see, 3 e to the 3 minus minus 3 e to the 3 plus e to the 3, and then that, oops, that minus 3e minus 1 e to the 1 is e, and then plus e to the 1. So let's see. These cancel. So we're left with, this is 2 times e squared minus 3.